Hello there, children. Today we are going to continue work on section 3.4, exponentials and solving log equations. So we're going to get going with this. So we talked about earlier about what happens if things have the same base. It's not that big of a deal. We use the one-to-one property of logs or exponentials, and we're golden. But what happens when something like this occurs? We get 4 to the x equals 15. I have an issue in the fact that we can't solve this one by making them have the same base. Sure, I can make 15 be 4 to some power, but the problem is it's kind of hard to figure out what that power is going to be. I mean, you could do it on the top of your head and be like, 1.95. You know it should be close to 2 because 4 squared is 16 and 16 is close to 15. But we can't use like what we did earlier. So what do? We are going to do the following. We are going to use the other form, namely log form. So we take this and we go, you know what? Don't particularly like this form. It's served its usefulness. And because my exponential is alone here, I am able to do the following. I am able to take it from exponential to log form. The way you can think of it is the base always stays the same. Log base 4 of 15 equals x. Or you can think of it this way. You always start at the base and go base 4 of 13, grab the equal sign, equals x. You can do it that way. Now look, the x is isolated by itself. If you can put this directly in your calculators, then you're set. If you can't, you've got to use what we did in section 3.3, ln of 15 over the ln of 4, or log of 15 over the log of 4. And then we can use our calculators and figure it out that way. And then we go ahead and solve this, rounding to 4 decimal places. Not too bad at all. The same rules apply for logs. I have a log with the x in the interior. Therefore, what I do is this form has exhausted all of its usefulness to me. So what I'm going to end up doing is turning it back into an exponential. The base is 5 in my log, so the base is 5 in my exponential. 5 to the second equals 2x. Notice how my x is now isolated. That's pretty good. I get 25 equals 2x. That means 25 over 2 equals x. And I go ahead and check that answer real quick in here to make sure it doesn't make the interior or the argument of my log negative, which it does not, so I may continue. Thus, that's the answer. Alright, so this problem with a nice tan background here, my x is in the argument of my log. So I want to turn it to an exponential, but before I can do that, I've got a slight bit of an issue. That 4 out in front is a problem that I am going to now have to deal with, because remember, the only time I turned anything into logs or exponentials is when they were isolated. This is not isolated, for I have a coefficient out in front. Therefore, I have to divide by 4 first and foremost to start the problem in order for this to work. So I go ahead and do that. Now, my log is isolated. Sure, I have different things in my argument here, but this is isolated. That's what I was looking for. Now I can turn it into an exponential. 3 to the third equals 2x plus 1. That's 27 equals 2x plus 1. I subtract 1. Divide by 2, and I get x equal to 13. Put that back into my problem. It does not make the inside of my log negative, thus it is the correct answer. So then I move on, which is a good thing. Now for this particular problem, first and foremost, what I've got to do is I've got to subtract 3. Because of the fact that this exponential has the x in the exponent, which is great, I know I can get rid of that by switching it eventually, but it's got that plus 3 at the end, so I can't switch it until I get rid of it. Again, the variable must be isolated, or rather, the thing with the variable in the exponent must be isolated. That base can't have anything behind it or in front of it. Now this is good here, so I turn it into a log, which is the log base 4 of 6 equals x plus 1. Now right over here, you can change your base. I'm going to use ln because I'm too lazy to write the word log. But you could. So you find out what this particular item is. When I do this, I get 1.2924. Now I know what you're saying. You're like, hey, wait a minute. You kept more decimals there than you did last time. You're right, I did. Because I know I'm going to have to round at the end. I don't want to keep intermittently rounding. Now, if your calculator does that, you can deal with that. And then I subtract 1 from this. And that's the point where I round. So I get x equal to here 0.2925. That's when I round at the end of the problem. So that's not overly terrible. You can put that back in to check if you'd like. Now realize though, when you check this back in the problem, since we end up rounding this number, when you take 1 plus that number, you're going to get something that we rounded. You take 4 to that power and add 3, you might not get exactly 9. You might get 9.00 something. So you have to realize that when you do that, you might not get the exact answer, but you're going to get something extremely close. So just be prepared for that. So for this problem, what I've got to worry about is, I've got to do a couple operations before I can go ahead and work with this. So the first thing I've got to do is I've got to subtract 1 from both sides. Just like you're solving a regular old equation like we used to do, 3 times my unknown that I want, plus 1 equals 8, you have to go ahead and isolate it. Which is exactly what I'm going for here. Then I'm going to divide both sides by 3. Now, what you cannot do at this point, you're not allowed to multiply that 3 in there because they have different bases. Even when they have the same base, you've got to be careful about, as you well know from exponent properties from Algebra 2, adding to my exponent there. But most certainly you can't do that if they have different bases. You do not want to get in that dangerous habit because it will not work out well for you. And that would be sad. Now from here, we go ahead and turn this into a log. Log base 1/2 of 7/3 equals x. So you can change the base here. Again, I'm going to use ln to change my base, just because I feel like using ln. Now again, I can change the base to whatever I want, but the only ones I really want to change that to are ln, which is log base e, or log on my calculator, which is log base 10. I really don't want to do anything else, because if I'm changing the base, it means my calculator can't do those other bases. Now, those of you whose calculators can do different bases, you're in luck. You can go ahead and do this particular problem without a wonderful and glorious change of base formula, which is not required. And you get negative 1.2224 equals x, which, if you think about it, kind of makes sense. I am taking a fraction, timesing it by 3, plus 1, and I'm getting 8. The only way that's going to happen is if this fraction somehow flipped around to a number greater than 1. And the only way it's going to do that is if my exponent ended up being a negative to flip it. So that's a good thing for us. Now, one thing I do want to show you is the following. Your book does this a little differently. This is the way I show it on the left, turning it into an exponential. Your book talks about exponentiating to both sides. So they use these things as exponents and use our properties of logs. E to the ln cancels that out, brings the x down. Look at this. So they take and use these two things once you have it isolated as an exponent. So if you look in your book, that's the way it's showed. I simply just say turn it into an exponential right away and do it. Both are correct. If you want a different way to do it, if you like that a little better, you're more than welcome to do that. I just think sometimes it might complicate it for you. We will use this property later on this section, though, in order to solve. You are now ready for your homework. Oh, happy days are here again. Go ahead, forth, and do. Hooray, math! Fin.